In this video, we're going to break down econometrics, the powerful tool economists use to turn data into real-world insights. You'll learn what it really means to build and test models, interpret regression results, and use data to make smarter economic decisions. But here's the thing. If you skip the basics, econometrics can feel like a completely different language. Don't worry though. By the end of this video, you'll not only understand it, you'll actually use it with confidence. So grab your notes, stay till the end, and let's get started. Econometrics is simply the part of economics that uses data and statistics to test theories and relationships. In simple words, it's how we move from guessing to knowing. Think of it like this. Economists have theories. For example, higher interest rates reduce investment. Sounds logical, right? But is it true in the real world? To find out, econometricians collect real data, interest rates, business investments, and time periods, then run a statistical test. If the data shows that when interest rates rise, investment actually falls, then the theory holds up. If not, maybe our assumptions were wrong. And that's how economic knowledge evolves. Here's another example. You might hear people say, education increases salary. Econometrics tests that too. Researchers collect data from thousands of workers, their years of education and income, and look for patterns. If the numbers reveal that people with more schooling consistently earn more, even after controlling for other factors, that's strong statistical evidence, not just opinion. So in short, econometrics turns economic ideas into measurable evidence. Visually, you can imagine two simple charts. In the first, as interest rates go up, a line showing investment slowly drops, a clear negative relationship. In the second, as years of education rise, salaries rise too, a positive relationship. That's the power of econometrics. It transforms economics from theory and debate into something scientific, where data speaks louder than assumptions. So the next time you hear an economist make a claim, remember, econometrics is what tells us whether it's true or just a theory waiting to be tested. Econometrics might sound complicated, but at its heart, it follows a simple three-step process, a logical path that connects curiosity with real-world evidence. It all starts with a question. Every great econometric study begins with something we want to understand. For example, does studying more actually improve exam scores? Or does raising the minimum wage reduce employment? It's that spark of curiosity, the "does X affect Y" question, that drives the whole process. Once we have our question, we move to step 2, collect the data. Here, we gather information about both X and Y, the cause and the effect. If we're studying grades, we might collect data on how many hours each student studied and the score they received on their exam. The goal is to have real, measurable numbers that capture both sides of the relationship. Then comes step 3, the regression analysis. This is where econometrics really comes to life. Using statistical tools, we run a regression to measure how strongly X affects Y. In our example, it tells us whether more study hours actually lead to higher exam scores, and by how much. The beauty of this process is that it turns intuition into evidence. We start with a question, collect the facts, and use math to discover the truth hidden in the data. That's the econometric process. Simple, logical, and incredibly powerful for understanding how the world really works. Imagine you're trying to understand what makes people earn more money. Is it education, experience, or maybe a bit of both? That's where regression comes in. It's like drawing a line through your data to see the overall trend and predict outcomes. Now let's make the key terms super clear and simple. On the screen, you'll see this first. Dependent variable, Y. This is the outcome we're trying to explain or predict. For example, income could be our dependent variable. It depends on other things. Think of Y as the result. Next up, independent variable, X. This is the cause or the predictor. It's what we think influences the outcome. For example, education level might be X, because we believe higher education leads to higher income. If you were studying marketing, your X could be advertising budget, and Y could be sales revenue. But in the real world, not everything fits perfectly on a line. Life has randomness. That's where the error term, or epsilon, comes in. It represents all the random factors we can't see or measure, things like luck, talent, or unexpected events that affect the result. Now, let's tie it all together with the regression line. This line is the best possible fit through all the data points. It shows the overall relationship between X and Y. You can think of it like this. The regression line captures the main pattern, while the error term explains the little ups and downs around it. So when we say Y depends on X, what we really mean is Y equals A plus BX plus epsilon, where A is the starting point, B shows how strongly X affects Y, and epsilon catches everything else. In short, Y is what we're explaining, X is what we think causes it, epsilon is what we can't predict, and the regression line is our best summary of how they're connected. Once you understand these, you've got the foundation for everything in data analysis, economics, and business forecasting. It's that simple. Now let's get into the heart of predictive analysis, the simple linear regression model. This is the most basic yet powerful tool we have for understanding relationships between two variables. The equation looks like this: Y equals A plus BX plus epsilon. It might look intimidating at first, but let's break it down in plain English. Y is the outcome, the thing we're trying to predict or explain. X is the input, the factor we believe affects Y. A is called the intercept. It tells us the value of Y when X equals 0. You can think of it as our starting point or baseline. And B is the slope. This shows how much Y changes when X increases by 1 unit. In other words, how sensitive Y is to changes in X. Finally, epsilon, that little Greek letter epsilon, represents all the random noise or other factors we can't perfectly explain. Because in real life, nothing fits an equation perfectly. Now, let's make this real. Imagine we're studying the relationship between education and income. Our regression model might come out like this. Income equals 20,000 plus 3,000 times education years. This means that even if someone had 0 years of education, the model predicts they'd earn around $20,000. That's our intercept, the baseline income. And for each additional year of education, income is expected to increase by about $3,000. That's the slope, the rate of change. So, if one person has 10 years of education and another has 12, the model predicts the second person will earn roughly $6,000 more per year. Of course, it's not a perfect rule. That's where our epsilon comes in. People's actual incomes will vary because of experience, location, luck, or other factors. But the regression line gives us the best overall fit, the line that summarizes the average relationship between education and income across all the data. That's the magic of simple linear regression, a clean, easy-to-understand way to describe how one variable moves with another, turning raw data into a meaningful story. Now that we've built our regression model, let's talk about what the results actually mean in the real world, because numbers alone don't help unless we can interpret them. When you run a regression, the software gives you an output with a few key values, things like coefficients, p-values, and r-squared. But don't worry, you don't have to be a statistician to understand what they're telling you. Start with the coefficient, often shown as b. Let's say your model shows b equals 0.5 for advertising. What that means is simple. For every 1% increase in advertising spending, your sales are expected to rise by 0.5%, assuming everything else stays constant. It's basically the slope of the line, how strongly one variable moves when the other changes. Next, look at the p-value. This number tells you whether your result is statistically significant, or in plain English, whether it's likely to be real or just random noise. If the p-value is less than 0.05, that usually means there's strong evidence your variable actually matters. So, if the advertising variable has a p-value of 0.01, that's a good sign. Advertising truly has an impact on sales, not just by chance. Another thing you'll often see is the R-squared, which tells you how much of the variation in your outcome, like sales, is explained by your predictors, like advertising, price, or promotions. For example, an R-squared of 0.8 means your model explains 80% of what's going on. That's pretty solid. But here's the key. Don't just look at the numbers. Think about the story behind them. If your model says a 1% increase in advertising leads to a 0.5% increase in sales, what does that mean for a real business? It means marketing is paying off, but it also helps you compare. Maybe social media ads perform better than print, or maybe discounts have a stronger impact than brand awareness campaigns. Regression isn't just math. It's a decision tool. It helps businesses answer real questions, like how much should we spend on ads? Or does pricing really affect demand? And the best part is, you can do all of this easily with tools you probably already know. You can run a regression in Excel, in R, in Stata, SPSS, or even Python. Excel is great for beginners. Python and R give you more flexibility and power as you grow. So when you see those coefficients and p-values, remember, they're not just statistics. They're insights about how the world actually works, and they can help you make smarter, evidence-based decisions in business, economics, or research. When we start working with regression analysis, it can feel like we've discovered a crystal ball. Plug in your data, run the model, and out comes the truth. But in reality, regression is only as good as the assumptions behind it. And when those assumptions break, our results can become misleading, even when the math looks perfect. Let's talk about 3 of the most common problems, the quiet troublemakers that can distort your analysis without you even noticing. The first one is omitted variable bias. Imagine you're studying how education affects income. You run the regression, and it shows that people with more years of education earn higher salaries. Great, that makes sense. But what if you forgot to include another important factor, like work experience or natural ability? Those missing variables are secretly influencing both education and income. And because they're not in your model, your results end up biased, giving too much credit to education for something partly caused by experience or talent. That's omitted variable bias, forgetting an important factor that actually matters. It's like baking cookies but leaving out sugar, then wondering why the taste feels off. Next comes multicollinearity. This happens when your predictors, the variables you include in the model, are too similar to each other. Think of it like asking both years of education and highest degree earned to explain income. Those two move almost hand in hand, so the model gets confused about who deserves the credit. In extreme cases, the regression still runs, but the individual coefficients become unstable. Small changes in data can flip the signs or blow up the numbers. It's not that your model is wrong, but it's like trying to hear 2 people talk at once and realizing they're saying nearly the same thing. The signal gets fuzzy. And finally, heteroskedasticity. A long word, but a simple idea. It means the spread of your errors isn't even across your data. Imagine plotting income against age, and you notice that for younger people, income predictions are pretty tight. Most people earn similar amounts. But for older people, the points scatter widely. Some earn very little, some earn a lot. That uneven spread means the variance of the errors changes with age. That's heteroskedasticity. It matters because regression assumes that all observations have equal reliability. When that's not true, your model's confidence, the standard errors and significance tests, can become misleading. You might think your results are rock solid when they're actually shaky. So in short, omitted variables hide the truth, multicollinearity blurs it, and heteroskedasticity distorts how confident we are about it. Regression is powerful, but it's not magic. Knowing these pitfalls helps you treat your results with healthy skepticism, not to doubt the data, but to understand it more deeply. Because in the end, good analysis isn't just about running the model. It's about making sure the story your numbers tell actually makes sense. You know, in real life, one variable is rarely enough to explain something. Take salary, for example. It's not just about how many years you've worked. Education, experience, Even things like job role or location all matter too. That's where multiple regression comes in. It's like upgrading from a simple line to a full map, one that shows how several factors move together to influence an outcome. The formula looks like this: y equals a plus b1, x1 plus b2, x2 plus dot 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 plus epsilon. Here, y is the outcome we're trying to predict, say salary. The a is our intercept, the starting point. Each b represents the strength or weight of a factor, those x's, and epsilon is just the leftover randomness we can't explain. For example, we might write salary equals a plus b1, education plus b2, experience plus b3, gender plus epsilon. Now, we're not just guessing based on one thing. We're controlling for multiple factors at once. This gives us a clearer, fairer picture of how each variable actually affects the result while keeping the others constant. That's the beauty of multiple regression. It helps us see the bigger picture, the way the world really works, where outcomes depend on many things all at once. So let's bring everything together. Econometrics is really where data, economic theory, and statistics meet. It's the toolkit economists use to turn ideas into evidence, to move from "I think" to "I can prove it." At its core, regression analysis is the heartbeat of econometrics. It's how we measure relationships, like how education affects income, or how interest rates shape spending. And the real goal behind all of this isn't just crunching numbers. It's about making better, smarter, more evidence-based decisions in the real world. So to put it simply, econometrics connects theory with reality, using data as proof. That's what makes it so powerful. Now, you don't just know what econometrics is. You actually understand how economists use data to prove their ideas. If you found this helpful, check the description for free resources and practice data sets I've added for you. And don't forget to subscribe so you don't miss the next video. Applied Econometrics with Excel, where we'll take these ideas and actually apply them step by step. Thanks so much for watching, and as always, keep learning smarter.